My dear students, one thing I forgot to mention about constraint optimization is that in order to cover the concepts related to constraint optimization, I'm basically following Alpha C. Chiang's book, chapter number 12. Now, in this video, I will cover two economic applications, and there we will again see how to form a Lagrangian function in terms of different kinds of given function with a budget constraint, and then we will be solving for the critical values. So this is basically to make your understanding better or more clear. So let's get started. Um, Here I'm taking a Cope-Douglas production function. So basically the Cope-Douglas production function is given over here as Q is equal to K to the power 0.4 and L to the power 0.5. And this is also subject to a budget which is equal to $108. As you can see, the two variables over here are capital and labor, and we are provided with the information regarding the price of capital, which is equal to 3, and the price of labor, which is equal to 4. That means, given these informations, we need to actually build up the constraint equation. Now we know that price of capital into the quantity we take and the price of labor and the number of laborers we hire, it is here basically faced with a constraint budget of 108. That's how this particular Cope-Douglas function is basically subject to this constraint. Now, the students of economics and also who have covered the Eco 202 course, they're very much familiar with this Cope-Douglas production functions. Let's see how to form a Lagrangian function given this information. So, in order to form the Lagrangian function, what will we do? Given the Cope-Douglas function, Q is equal to K to the power 0.4, L to the power 0.5, we will take a plus lambda and we will join the constraint or the subject to equation over here. So this is 108 minus 3K minus 4L, and that's how I have formed the Lagrangian function over here. Now let's elaborate it a little more. So K to the power 0.4 and L to the power 0.5 plus 108 lambda minus 3 lambda K minus 4 lambda L. Okay. Now let's differentiate it with respect to K, which is 0.4 K, and from the power of K we will subtract 1, and L will remain as it is. As we are differentiating it with respect to K, we are left with 3 lambda. So here we get 0.4 K to the power 0.6 L to the power 0.5 minus 3 lambda, and then we set it equal to 0, and this becomes the equation number 1. I'm sorry. In terms of L, we get K, we differentiated the given production function Q with respect to L, and what do we get? It is 0.5 which will come in front because we are now differentiating with respect to L, right? K remains as it is, and from the power of L we subtract 1. And then as we are differentiating with respect to L over here, so we are left with again 4 lambda. Set it equal to 0. From here we get 0.5 k to the power 0.4, L to the power negative 0.5, and minus 4 lambda, which is equal to 0. And this provides us with equation number 2. We will also take the first order derivative with respect to lambda. As a result, we will get q lambda is equal to 108 minus 3k minus 4l, set it equal to 0. And this is equation number 3. Just like before, from equation 1 and 2, we get 0.4 k to the power negative 0.6 L to the power 0.5 and 0.5 k to the power 0.4 L to the power negative 0.5, which is equal to, on the other hand side, 3 lambda by 4 lambda. Okay, so basically we are dividing equation 1 by equation 2. Okay, so what do we get over here? Over here, then we get, if this lambda and lambda crosses out, we are left with 0.8 k to the power minus 0.6 minus 0.4 and L to the power 0.5 plus 0.5. So see what I have done? I have taken these parts above. As k, the base is common, so I have just added or subtracted the powers. It was a positive power, so as it has gone up, it has become negative. And this one was a negative power, as it has gone up, it has become positive, right? On the other hand side, we get 3 divided by 4 is 0.75. And how do we get this 0.8? By dividing 0.4 by 0.5, we get 0.8. I hope this is clear. Now, from here, we get 0.8 k to the power negative 1 and L to the power positive 1, which is equal to 0.75. Or in other words, it is, if I flip it, if I keep L at the UCL and take K to the LCL, so K becomes positive. So L by K is equal to, then 0.8 goes down, so it becomes LCL here 0.8 and above is 0.75. Okay, so finally from here I get that L by K is equal to 0.94, or L is equal to 0.94 K. Now, if I put this value, L is equal to 0.94 K in equation 3, what do I get? 108 minus 3k minus 4 into 0.94k. Let me write it again. I have just made a simple mistake here, so I'll write it again. So yes, I'm putting it in equation number 3, where there was 108 minus 3k, and instead of 4L, I'm putting it putting this L here. So the 4L is simply 4 into 0.94k, and this was equal to 0. So now the whole term is in terms of k, which is, if I take k on the other side, it is 3k plus 4 into 0.94k. Okay, or 108 is equal to 6.3 as 6.76k. Okay, so from here I get k is equal to 16. This is the approximate value I'm providing to you. Okay, now if you have got the value of k, then you can automatically solve for L. I will not show it again. You do it by yourself. You will get 15, and then lambda is simply equal to 108 minus 48 minus 60, which is equal to 0. Okay, now remember that, as I said, that these two are the approximate values. Okay, so that's how you have identified the critical value. If you put it in the original production function, you will get the exact figure for production. Okay, now let's see another example. Or let me give one example for you. This is again a Cobb-Douglas production function with k to the power 1 by 4, L to the power 3 by 4, and this is subject to a budget which is $100, and price of k is equal to 5, price of L is equal to 2. So what you will do is at first you form the budget constraint. Okay, let's do it. It is very simple. This is as we know, pk into k plus pl into l is equal to budget. So this is 5k plus 2l is equal to 100. So form the budget constraint, and then also form the Lagrangian function, and also form the Lagrangian function. So if I form the Lagrange, then the Lagrangian function will look like q, so this q is equal to k to the power 1/4 L to the power 3 by 4 plus lambda into 100 minus 5k minus 2l. My bad, let me write it again. Sometimes it gets difficult using the Wacom, the device that I'm using, and writing becomes a bit tedious. Okay, anyways, so I have formed both the equations for you. Now, this is just a small homework. You do it by yourself. Identify the critical values. Okay. Now, the next economic application. Here, it is said that optimize the utility function. Okay, where u is equal to 5xy plus 8x y xz, sorry, 5xy plus 8xz and 3yz. So now you can see that this is a case of three variable where we get x, we get y, and we get a z. That's a three variable optimization case, and this is subject to a budget constraint, and where it is given as 2xyz is equal to 1920. Okay, what do we need to do? We need to form the Lagrangian. Okay, so the Lagrangian function will then look like u is equal to 5xy plus 8x, my bad again, 5xy plus 8xz plus 3yz. Okay, and then plus lambda into 1920 minus 2xyz. Now this time we need to solve for ux after forming the Lagrangian function. Okay, again you can elaborate it if you want. So you can write u is equal to 5xy plus 8xz plus 3yz plus 1920 lambda minus 2xyz lambda. Now over here, ux is, if differentiate with respect to x, we get 5y plus 8z minus 2 lambda x, sorry, not x, minus 2 lambda yz, 2 lambda yz, and set it equal to 0, equation number 1. Then you solve for y. If you solve for y, you get 5x plus 3z minus 2 lambda xz, set it equal to 0. This is equation number 2. Then you get u z, which is, if you differentiate with respect to z, you get 8x plus 3y, and then you get a negative 2xy, 2 lambda xy. Let me write it again clearly. So you will get a 2 lambda xy, which is equal to 0. Then set it as equation number 3. Now don't forget to differentiate it with respect to lambda as well, which is simply 1920 minus 2xyz, and you can set it equal to 0, and this is your equation number 4. I hope you haven't forget the necessary condition where always we need to take the first order derivative and set it equal to 0 to solve for the critical values. Okay. Now, if we solve for the critical values, then we will get x is equal to 6, y is equal to 60, z is equal to 10, lambda is equal to 0.5, and u, the utility function, is equal to 1440. And how do we get it? After putting the values of x, y, z in the given utility function. Okay, so also try to solve this by yourself. In the next lecture video, we will look at the maximization or minimization part. That means the optimization in order to identify that whether the function is at its relative maximum or minimum by taking the second order derivative. Keep tuned. Thank you.